So, welcome to network analysis course 54th lecture, and today I will be telling you about Thevenin's network. Any network, first I tell the statements across point A and B, and here is the network having several sources, several current sources, it might be there, all are interconnected R, L, C, whatever it is. Then this network, looking from this end into the network, can be shown to be equivalent to, behind all this complicated thing here, a single impedance which is called Z Thevenin's, and in parallel in series with a voltage source V Thevenin's, and here is your point A B. Therefore, any network, given network, can be converted to this across a pair of terminals. Then if you connect some load impedance here, if here load impedance is connected, so current in the circuit will be V Thevenin's by Z plus Z Thevenin's. That is the idea. Clear? Now, why it is so? It is because why can we represent a linear network in this fashion across a pair of points? The idea is once again similar. Suppose here the impedance is connected Z, which is external to the network I have connected across AB, chosen a points where I have connected a network I. So, if you connect it, this current suppose will be I, and I can get that current by applying any method, that is the thing. Now, we have learned here once again I will use the concept of substitution theorem. So, here is the point A and here is the point B, and all the sources are present in the network, several current voltage sources, several circuit parameters, all in S domain I can convert and write it down. So, across AB, so here maybe V Thevenin's S, Z Thevenin's S, Z Thevenin S, like that, this you will get I S. So, in general I am writing. Now, this is AB. Now, in the actual network there will be this impedance connected, and in this branch a current I is flowing. Therefore, I can replace it by a current source I, is not? That is what from, and nothing will change, all the branch currents in this network, in this path, they will remain unchanged if you replace this by current source. Then what you do, calculate VAB, voltage across this impedance, by superposition theorem. That is the thing. To calculate by superposition theorem VAB, what I will be doing, this is the network. In this network, first step, I will say that all sources internal to the circuit are present, all the parameters, everything are there, and the current source is at present. First step, calculate VAB due to all the internal sources. That is, all the internal sources are present, and this current source should be replaced by its internal impedance. It is an ideal current source. So, its internal impedance will be infinite, open circuited. So, I will calculate VAB in this network for all the internal sources, and this is called V Thevenin's or V open circuit voltage. So, given this network, calculate what is VAB when all internal sources are present, nothing is connected here. That will give you V Thevenin's. Then second step is only the external current source that is I is present, and all the internal voltages, all the internal sources replaced by the internal sources replaced by the internal impedances. What will be the network? So, for step 2, the network then will look like all the parameters will be there R, L, etc., but voltage source should be replaced by short circuit, current source should be replaced by open circuit, and here is only your this current source present I, and this is the point A, this is the point B, is not, that will be the thing. Now, here is a current source which enters here, comes out through A. Therefore, here there is no sources now, therefore, it between A and B, this network will have some equivalent impedance. So, between A and B, I will say this is nothing but the equivalent impedance of the network across A B and here is the current source. And this equivalent impedance looking from this end into this side is once again that Z Thevenin's, is not that will be the thing. So, this current source is present and this is the thing here. So, I first calculated V Thevenin's OC. So, what will be this voltage? This voltage will be, this is plus, this is minus Z Thevenin's into I. So, VAB under this condition with this potential of this with respect to this is minus B to A you go minus Z Thevenin's into I. Therefore, VAB when this current source and all the internal impedances are present, that will be then equal to. So, VAB when all the sources are present will be equal to V Thevenin's, that is open circuit voltage, minus Z Thevenin's into I, the sum of these two, is not, this will be this voltage present. But in the network I know this voltage, this is the situation, original network situation. Here was a current source, this I replaced by current source. So, this is the network, this voltage and this voltage are same when all sources are present. Therefore, this must be equal to this V, but what is this V? This is I into Z. When because I assumed okay, this was the network, Z is connected, current is supposed to be I. So, what is the voltage between these 2 points? I into Z. When everybody is present, then this I Z should be equated to this, and from this I will say that current to the load, if you bring it to this side, is nothing but V Thevenins divided by Z plus Z Thevenins. This is the final thing. That is the thing here. Therefore, you see, however complex the network is, the theorem states that across a given pair of points of your choice, you may be interested to know what is the Thevenin's equivalent of this big network across points A and B. To find out that, what you have to do is this: you have to find out the equivalent impedance of this network with all internal sources replaced by their internal impedances. That is what I have to do. Z Thevenins I will get and I will try to find out V Thevenins by calculating nothing is connected across AB, open circuit voltage because of all the internal sources. For that, of course, I have to solve the network. When all sources are present, I know how to calculate VAB, and that I call V Thevenins, and you will get that. So, a simple example. So, we took a previous example 644. Let us do that. So, suppose I say that I have a network 24 volt. Here, what was the resistance? 6 ohm. Some 6 ohm is there. Here is some 4 ohm. I say that, let us take a simple example, this one. I say that find VAB, Thevenin's equivalent of this network, Thevenin's equivalent of this network across AB. So, first thing what I have to do, I have to calculate P Thevenins. Nothing is connected across AB. This is the network left hand side. So, V Thevenins will be simply 24 by 10 is this current, that is 2.4 ampere, is not, and this into this resistance 4 ohm. So, into 4, this will be the voltage, with this is plus, this is minus. So, how much it will be? 2.4 into 4, 9.6 is it? 9.6 volt. That is the one thing. Second thing is, what will be the R Thevenins? R Thevenins will be, redraw the circuit with all internal sources replaced by their internal impedances 6 ohm, this is 4 ohm, and these are AB. Look into this network from this end, find out what is the R equivalent, which is very easy. 4 and 6 are in parallel. So, 4 into 6 by 10, that is 2.4 ohm. Then I will say the Thevenin's equivalent across AB, you can think that A B. You want to find out current, if you have connected 4 ohm, okay, it will be 9.6 by 2.4 plus 4 ohm. So, this is the Thevenin's equivalent network of a circuit. So, I have taken a very simple example to highlight the main steps, and you get these values. Now, sometimes while solving problems to find out particularly R Thevenin's, so Norton's and Thevenin's theorem are reciprocal things. So, this thing we have already seen in our very initial lectures. A voltage source in series with an impedance can be replaced by a current source 9.6 by 2.4, that is the short circuit current. So, what is the short circuit current? 9.6 by 2.4 if you short, and in parallel the same resistance. And this is your Norton's equivalent, so much ampere. Therefore, if somebody has already got Thevenin's theorem, translating into Norton's theorem is no problem, or you have got Norton's theorem, then come back here very quickly. But nonetheless, sometimes Norton's theorem is also helpful. You should be very careful. I mean, try to adopt a method, whether should I find out Thevenin's equivalent or Norton's equivalent, it depends. You look at the circuit and try to find out. But what I am telling is now this thing, that sometimes the calculation of Z Thevenin's become somewhat complicated. For example, if I say I have a network like that, more on calculation of Z Thevenin's or R Thevenin's. You understand what do I mean by Z Thevenin's? In S domain also it is Z Thevenin's S, R Thevenin's. So, if it is resistive circuit, suppose you have a circuit like this. There may be situation when you have disconnected all the networks. To calculate the equivalent resistance, series parallel rule may not always apply. You may find that resistance between any 2 points very difficult to compute. For example, if I say that I have an, while calculating R Thevenin's, if I ask you calculate R A B here, why I have done this? Because in some circuit I found to calculate R Thevenin's between some 2 points, circuit looks like this. Then how to find out the R Thevenin's, that is R equivalent looking from this end? You see, it is very difficult. I do not know. Suppose this is R 1, this is R 2, this is R 3, and this is suppose R 4, this is R 5, this is R 6. I am not sure, I cannot apply series parallel rule here, because I cannot say R 3 is in parallel with this combination, but whether R 4 or 6 is in series? No. So, somewhat difficult in this situation, particularly in this form if the impedances appear. We know that if two resistances are connected in series, R 1 plus R 2, parallel R 1 R 2 by R 1 plus R 2. Similarly, in Z 1, Z 1 Z plus Z 2 or Z 1 Z 2 by Z 1 plus Z 2. But sometimes what happens, impedances may appear to be connected in this fashion, then calculation of RAB is not impossible, but looks like difficult. Suppose there is a one way of solving this problem. If you find you cannot decide upon whether the resistances are connected in series or parallel, you have to find out the impedance looking into the circuit. So, best thing is then you apply some voltage between these 2 points, find out this current, apply some known voltage V, apply some known voltage here and see how much connect an ammeter here and see what is the current drawn by this network. In fact, you don't even don't try, nothing is known about how these impedances are connected. One way of doing is apply some voltage, see how much current it is drawing from the supply. Then we will say R equivalent from these 2 points across AB will be V by I. That way it can be solved by, that is, you have to solve another network now. Apply some known voltage, see how much current it is drawing, and then this V by I will give you the current. That is one way of handling this equation if it is DC circuit. But what I will tell you in general, what happens is this: I will tell you about the star delta transformation. This I never told earlier, star delta transformation. Where it will be useful to calculate equivalent impedance. The point I want to tell is this: suppose you have got 3 points, okay, 3 resistances. This has nothing to do with Thevenin's theorem, but it will be very useful. Suppose you have 3 resistances. Say R A, R B and R C, R A, R B and R C. And these 3 points are A, B and C. I ask you, okay, with respect to these 3 points, A, B, C points are fixed. I say that this is R 1, this is R 2 and this is R 3, and I say these 3 points remain same. In other words, what I am telling, 3 resistances known value R A, R B, R C, they are connected in star. Can they be replaced across these 3 points by some delta connected resistances? So, R A, R B and R C are known. Question is R 1, R 2 and R 3. How I can calculate and replace these star connected impedances by R 1, R 2, R 3? That is the question. That can be easily done in this way. Suppose, okay, if these 2 networks, if these 2 things has to provide you equivalent impedance. So, R A B, suppose between points A and B only, what is the equivalent resistance of this network? At the point C, I have not connected anything. So, it will be R A plus R B, is it? R A B. If nothing is connected at C, it will be R A plus R B. And this R A B, if these 2 are equivalent, must be same if you see from this end what is the equivalent impedance. At C nothing is connected. Now, in this circuit this must be equal to this R 2 and R 1 plus R 3 are in parallel. So, I will write R 2 into R 1 plus R 3 divided by R 1 plus R 3 plus R 2. So, R 1 plus R 2 plus R 3. Mind you, this can be replaced by Z s, because V s equal to I s into Z s as V equal to I r. So, no problem. So, this is one equation. Similarly, across B c, if you calculate R B c from this circuit and from this circuit, they must be equal, then only these two will be equivalent. In that case, B and C, A you have connected nothing. So, I will say R B c with nothing connected to A is R B plus R C, and this should be equal to R 3, it will be in parallel with R 1 and R 2, is it? That is R 3 R 1 plus R 2 divided by once again R 1 plus R 2 plus R 3. This is equation 2. Thirdly, across C A, I will calculate resistance, equivalent resistance with nothing connected to B here and in this circuit. What is the equivalent resistance here? R C plus R A. And this must be equal to across R C, it will be R 1 in parallel with R 2 plus R 3. So, R 1 into R 2 plus R 3 divided by R 1 plus R 2 plus R 3. So, I have got three equations, R A, R B, R C are known, and here is R 1, R 2, R 3. So, I will be able to solve it, but nice way to do it is this way. Suppose you add all these three equations, you see, you add all these three equations, that is 1 plus 2 plus 3. If you do, on the left hand side you will get 2 R A plus R B plus R C, and on the right hand side denominator is same, R 1 plus R 2 plus R 3, and on the top you see R 1 R 2 appears 2 times. Similarly, R 2 R 3 appear 2 times. It will be 2 into R 1 R 2 plus R 2 R 3 plus R 3 R 1. You know, this will be the thing. This 2 goes. So, R A plus R B plus R C is equation 4. No new equation, just adding these 3. In which way it will help me? You suppose say that I will do 4 from this equation 4, I will go on subtracting equation 1, 2 and 3. So, 4 minus 1 you do. If you do 4 minus 1, on the left hand side you will be left with R C, 4 minus 1. Below it is R 1 plus R 2 plus R 3, no doubt, and this minus this R 2 R 1 and R 2 R 3 goes, R 2 R 1 and R 3 R 2 goes, you will be left with R 3 into R 1, is not. So, R C will be R 3 into R 1 by R 1 plus R 2 plus R 3. Similarly, by subtracting 4 minus 2 etcetera, what you will get is R B is equal to R 2 R 3 by R 1 plus R 2 plus R 3, and R C RC I have got RA will be equal to R1 R2 divided by R1 plus R2 plus R3. It is easy to remember. Suppose I am now telling that if R1, R2, R3 are known, then equivalent star representation I will be able to calculate quickly. That is, this one can be represented by one RA here, that is RA. This one can be replaced by RB and this one can be replaced by RC. What will be the value of RA? This one, product of these two, R1, R2 divided by sum of these two. What will be RB? R2, R3 divided by sum of these three. What will be RC? RC will be R1, R3, R1, R3 by R1 plus R2 plus R3. Therefore, this is called, this will be helpful delta to star conversion. Okay. So, similarly, you try yourself. In the next class, I will just tell another few lines will be necessary to calculate the reverse one. That is, okay, if RA, RB, RC are known, then what should be the R1, R2, R3. So, I will take up that in the next class and then also come back to other interesting network theorems. Thank you.